Morning, everyone. So yesterday we started into our waves chapter. We took a look at the different types of waves. We categorized them either as electromagnetic waves. Those are waves like light that can travel through a medium, but they don't need it, compared to sound waves, which actually travel through a medium of air. Were it not for the air particles that actually vibrate in between, you actually wouldn't be able to hear the things that we're saying here. We also talked about the waves. Waves, their job is to transfer energy. So on this summary diagram that I have here, waves will carry energy or transmit a signal from one place to the other without any permanent displacement. So unlike tossing an object over where the object actually physically moves and permanently is pushed away, a wave, in this case here, your particles might actually only be bobbing up and down. Whenever you have particles that are moving perpendicular to the motion of the wave, we refer to that as a transverse wave. While if I use a slinky here, I know this wave here, as I've drawn it, is heading to the right. I might be able to squeeze the slinky here, and then as I let go or push it back and forth, there will be places that are squeezed together, some places that are stretched out, and that can also transmit the signal. The particles themselves are traveling parallel to the motion, but no one particle actually physically permanently gets displaced, so therefore it's still considered a wave. That would be a longitudinal or a compressional wave. So sound waves would be an example of that one. A couple other little definitions for us here. So for a wave, you can picture this as a water wave for now, so we don't have to have like a metaphorical wave, but we have all the tops of these waves here. We mentioned they were called crests. We have the troughs that are on the bottom here. We measure the amplitude, which is the maximum distance away from the no wave case. The no wave case, sometimes you call it the equilibrium line or the rest line. And basically we can measure this amplitude is a measure of the energy. We're going to see in today's lesson, as we study more of the wave phenomena and different interesting things that waves do, the amplitude is actually a function of energy, and energy actually, let's say in the sound example, it gives you the volume, and the light example, it gives you the brightness or the intensity. That is a measure of the energy that we're going to see. The other way energy can be transmitted by this wave here is via the frequency. If you were over here and you were holding a slinky, you can oscillate. So oscillate means moving it up and down. You can oscillate at a very slow frequency up and down, like a really slow skip rope, or you might be bobbing up and down really, really quickly. You can also transmit the same signal, but at a higher frequency. In the sound analogy you're going to see later on, it's going to have some impact on the pitch, the actual, the note that comes off of it. And then in the light example, it actually gives us the different wavelengths. It gives us different colors of light. I mentioned again, we did talk about electromagnetic spectrum. This one does not require a medium. We wrote this down yesterday. It does not require a medium, but usually we are on the Earth. Usually it has to travel through the atmosphere. Usually it is going to run into something. That's okay. Electromagnetic spectrum, or these waves here, they don't require one, but they can travel through one no problem. We're going to see in an upcoming lesson, as it goes through the medium, it sort of runs into particles and it has a hard time traveling through media, and things tend to slow down. We had the electromagnetic spectrum here. We talked about the visible portion. The Roy-G BIV here is actually a really, really tiny fraction of a much wider spectrum. We had categorized here UV light, X-rays, gamma rays. On the other side, infrared, micro. You can look back in your notes for that. Today, I just want to flesh out a few other sort of measuring numbers that we can use for waves here, and just show you an example calculation. So yesterday, we started taking a look at, in fact, all these forms of light here, whether they're visible or invisible to us here, all forms of light travel at the speed of light. This speed here assumes that we're in vacuum. This speed assumes that we're traveling through the nothingness of space. We had derived the first expression, which we call the universal wave equation. This one here is on your formula sheet here. Just want to emphasize to you how this came to be. Imagine I had a water wave. So here's my water wave. I just took a picture. That's the water wave at time 0. And let's say this water wave here has pushed exactly one wavelength pass. So here's my water wave here at the new time. So in this case, I would say, well, velocity is supposed to be distance over time. If I just sort of highlight a sort of fraction of this one here, my wave in picture number 1 started over here. As time has ticked onwards, we've actually gone exactly the distance here, and I've tried to mark off a distance here. Let's say it's traveled exactly that lambda, and that lambda here is actually our wavelength. So in this case here, we have traveled through a distance of lambda. We traveled through that length before we repeat ourselves. And then the question here is, well, what the time would have been if I were sitting on this water wave here. As this wave here pushes downwards, I would have followed the wave here downwards. As it pushed past me, I would have went all the way up as this crest here passes me, and then I come back down here towards the equilibrium position. You're going to find that by the time this wave here is exactly overlapped with itself, we would have gone through one complete up and down motion. We had timed that there. This time here was called the period. Again, you can't necessarily take a picture of that because that's measured in time. But this time here is actually t, which is period. So if I did, the wave actually physically traveled by one wavelength worth of distance. We divide it by the period here. We remember from yesterday's lesson here, 1 over period, the reciprocal period. The upside down of period is actually frequency, and this is actually where they get the universal wave equation, V is equal to lambda f. It's just in our case here, when we're using light as an example, as we're doing this problem here, light is traveling at the speed of light. They use the constant c instead, and we can treat that as a constant here. So that's actually where we derive. This formula here is called the universal wave equation. This one here applies to light as well as sound and all different types of waves here. And it basically says V is equal to lambda f. If I translate that in words for you here, like say in the light example, all light travels at the same speed. So in this case here, whether it's a high energetic UV photon or a low energy radio wave, this one here is a constant. So therefore what we're going to see, if light is going to zip by you at exactly the same speed, we're going to find there's an opposite relationship between these two here. In fact, as the wavelength here shrinks, as the crest to crest distance, at first it may be something like this, and then maybe I go to a more narrow wavelength here, this photon is going to still zip by you at exactly the same speed. If you were on a metaphorical boat, you would rock up and down less times when the wavelengths are far away from each other, but when the peak-to-peak distance is a lot closer, you'd bop and down, oscillate up and down much more quickly. It's demonstrating to you an inverse relationship here. I wrote this down last day. The wavelength and the frequency. Careful for frequency, sometimes they use the symbol nu for it. It's like almost like a squiggly U. Wavelength and frequency are inversely related. They are opposites. And you see in the summary diagram that I pulled up for you here, as we see that the wavelength is getting shorter and shorter, going from the thousands down to the 0.0001, right? As the wavelength is getting shorter, we see that the frequency actually increases. These two are actually opposites. I want to introduce you one other formula here. This is specific for light here. This is called the Planck Equation, and we can actually figure, because waves their function is to transfer energy, depending on the frequency, we see actually a direct correlation. The higher the frequency, the more times I bob up and down, like this wave here, I'm going to oscillate up and down very many times. That's actually going to carry more energy. So again, frequency is another way of tracking these sort of wave numbers here. This first equation, we called it the universal wave equation. The next equation here, specific for light, we can call it the Planck equation. And this just demonstrates a proportional relationship for us here. The energy carried by a wave, it's proportional through h, which is Planck's constant, multiplied by the frequency. In this case here, I'm going to give you this h here is Planck's constant. And this one here turns out to be a very small number, 6.63 times 10 to the negative 34. In terms of units, what it has to have, frequency would have been measured in hertz. Frequency would be like a seconds to the minus 1. It'd be like a per second. Energy, we've seen in the last chapter, energy is supposed to be in joules. The Planck's constant unit has to give you the joule that energy has, and actually has to get rid of the seconds to the minus 1. So in this case here, Planck's constant is quoted in joule seconds. And that way this seconds here will cancel the second minus 1, and we'll pick up the joules. So in that case there, we have these two formulas here. Again, this is specific for light. So let's just do a quick example. Let's say I am looking at a radio wave. I know that would be invisible to me. Radio wave with frequency, let's make it here 2.0 times 10 to the 4 hertz. Right? So again, what that's saying here is the wave is at such a sort of peak-to-peak distance that if I were on a metaphorical wave, in every second that passes by, I actually bob up and down some 20,000 times. Now, light is zipping by us really quickly. That 20,000 may seem really ridiculous, but as we get to sort of visible light and UV light, we're going to see this frequency go up to like 10 to the 12, 10 to the 16 or so. This is a relatively small frequency because relatively speaking, the wavelength is fairly long. What I want you to do in this problem here is I want you to calculate some of the other numbers. So I want you to calculate. Let's calculate the period, just like we did yesterday. Calculate the wavelength, and now we can actually calculate the energy of this photon. Even though it's invisible, it is transmitting energy from the radio station to your whatever device you're running. So let's think about the formulas we have so far. Yesterday we knew period and frequency are opposite of each other. I already have the frequency, that's not too hard, just take an upside down of that number. For wavelength here, we're going to use our universal wave equation. C is equal to lambda f. Because I have f and I know the speed of light, I can find this lambda here. And the last one here will be an application of Planck's constant here. E is equal to hf. Again, because they've already given me f, I can punch it through Planck's constant, and therefore I have the energy there. Sometimes they ask it sort of in order. They might give you the period, you do the reciprocal of it, find the frequency. With the frequency, you can either go to energy or go to speed of light. So let's just try this out here. Not too bad in terms of number crunching. 1 over this 2.0 times 10 to the 4. This one here gives me 2e4. This gives me 5 times 10 to the negative 5. Period is measured in seconds. So this is, just let me translate this for you here. This is the time for one cycle. Because I am bobbing up and down some 20,000 times, if you give me 1 whole second of time, I'm actually, if you give me 1 whole second of time would be the bobbing up and down 20,000 times. For just one bobbing up and down motion, it'd be something much less than 1 second. So this is 0.00005 seconds. For the speed of light here, we're going to use 3.0 times 10 to the 8 for that c. The lambda here we don't know yet. We don't know the wavelength, the crest-to-crest distance. We expect it to be relatively big because this frequency in the grand scheme of things is actually fairly small. I'm going to divide it by 2 times 10 to the 4. And therefore we get our wavelength here. 3e8 divided by 2e4 gives me here 1.5 times 10 to the 4. Lambda is a distance, so this is measured in meters. So the reason why radio waves carry so little energy, their peak-to-peak distance here is in the kilometers, believe it or not, 15 kilometers worth. So you need to go 15 kilometers before you actually measure one crest to the other crest. Why am I still able to bob up and down so many times? Again, it's because light is zipping by you really quickly. So even though the distance peak to peak is huge, because it zooms past you, the wavelength, the frequency here can still bob up and down quite a few times. Let's also link this here because I do have the frequency. Let's proportional through Planck's constant, 6.63 times 10 to the negative 34. Let's multiply it by this frequency here, 2.0 times 10 to the 4. And this one here just sort of rescales that number for us here. Planck's constant by itself is very tiny, so we're expecting to get a very small energy off of this. This is the energy per radio photon. This one here, believe it or not, like it looks like a tiny number, 0.000, right? It looks like a tiny number, 10 to the negative 29. But this is just the energy for one. Energy for one, you can say photon, or in this case here, one radio particle. At any given point, the radio station is transmitting many particles at a given time. This energy here stacks up very quickly. So hopefully that fleshes out a little bit here. We can actually say this Planck's constant here in words. I already sort of alluded to it here. Frequency and energy are just proportional. They get rescaled through Planck's constant. So a word way of describing this Planck equation is we can say the energy and the frequency, how much energy that your wave carries, and how many times I bob up and down are directly proportional. These ones here, when one gets big, the other gets big. So what I want to do in this lesson here is just demonstrate to you some of the variety that waves can come to us in. Waves can actually come to us in multiple different shapes. So far we've only done the sinusoidal shape. So if you're in math class here, you're going to see the sine function and cosine function here follow this sort of orientation. That one, there's definitely a sinusoidal function. Sometimes waves are more, they call this a sawtooth wave, so it's kind of jagged and sort of zigzag like this. Sometimes waves come to us in a sort of square wave, so it could be a square wave that this sort of goes perpendicular like this. When we actually get our energy off from the electrical sockets from the walls, the current that we're actually getting actually alternates like this. We get AC current. We design other devices that actually only let through current in one direction, and we basically eliminate some of these bottoms of the waves, and we can transition AC to DC, so we can actually play around with the shapes of these waves as well. Before I just summarize for you like a few more properties of waves here, we're going to switch gears here, and I'm going to show you a quick simulation. I'll link the simulations online for you so you can play around with it some more, but I just wanted to show you some of the different phenomena that waves can actually participate in. So here's our first simulation that we're going to do. We have a wrench on this sort here. You can actually drag this wrench here up and down manually, and you can generate a wave. I'm just going to restart that there. What I'm going to do is I'm going to set this wave here to oscillate. So it's going to be actually put on a motor. It's going to actually bob up and down like this here. It's a little more complicated because I do have a fixed end on the other side. Just for simplicity for now, let's say we have no end. Let's just send this wave here off to infinity. Here I am with my slinky analogy here. I'm oscillating it up and down. The wave, the energy is being transmitted to the right. But you'll notice, like in a real world question here, we always have some dampening, some sort of friction to it. In this case here, we have a fairly little damping. If I have much damping, this one here will die off really quickly. If I have no damping, that's the case we're going to start off with here. That's the perfect world. It's like the pendulum that can rock back and forth forever. So no damping. A couple things I can change here is the amplitude. I can change how far up and down my arm moves. The bigger the amplitude, the more energy. Again, in the sound case there, that would be higher volume or smaller amplitude there. The other way I can transmit energy is with the frequency. Frequency is that number, how many times it's going to bob up and down. I can increase the frequency to cause more waves at a time. That carries more energy, a higher pitch sound. Or I can decrease the frequency here. Because this is a mechanical advantage like a slinky, I can play around with the tension. The tension here decides how quickly this wave here can transmit itself through this slinky here, and that sort of deals with a little bit Hooke's law kind of material wave. So let's just start off here. I'm going to reset this. I'm going to, instead of doing this oscillation motion, instead of doing the full up and down motion and seeing this repeating, this periodic nature, what I'm going to do is I'm going to send in a pulse. So here's how this is going to look like here. I'm going to start the pulse. I'm actually going to pause it so we can just step through in time. Right now we're at the default amplitude, default pulse. So I just push that there. This pulse here had gone upwards. Oh, sorry, I actually wanted to lower the dampening here. Let's try it one more time here. Let's reset that. So pulse. I want to actually do the ideal case so you can see a little bit better here. I'm going to pulse it and I'm going to press pause. So this pulse here had gone up and it stopped here. So it's only sending in here a triangular wave on the top. This wave here is going to go all the way down. It's going to transmit my energy. Right now I have a few choices on the other end. Right now this choice here is what's called a fixed end. It's like your friend is holding the slinky really tightly. I want to see what happens to this triangular wave here as it hits the other end. So I'm going to just step it forwards here. As it interacts, the green particles and the red particles are demonstrating the slinky themselves are moving perpendicular to motion. Hopefully you can tell me that that one there is a transverse wave. You'll notice when I hit the end, because that end is held tightly, it doesn't let that green particle there move. That will later on be called a node. Let's watch what happens afterwards is upon hitting a fixed end, just going to run the clock a little bit here, whoops, it actually flips to the bottom. So it actually reflects off of a fixed end here. So let's just keep going to the other side here. This one, because I'm not oscillating anymore, also represents a fixed end. I would imagine this one here would then end up going back to the top. So it reflects on any fixed end. Let's imagine we have a loose end instead then. So again, an upwards wave here. We send it down. Let's just stepwise go across it. You can play around with this some more. This time, because this end here is loose, this green particle is actually allowed to move. And as it moves here, it notices this green here actually goes upwards, and it's actually going to let the wave go higher. And you notice the wave coming off of this ends up staying on the top. Although it does reflect back to the left, it does stay on the top. As I run the clock here, this is going to run to the closed end again. I would imagine it goes to the bottom. Let's see if that's true here. I press play. There we go. It's on the bottom. It hits the loose end again here, and it stays on the bottom here. All right. So I'm going to watch what happens here. So this time here, I just stepped through a loose end. This wave here is now coming backwards to the left here. It's on the top. What's going to happen here is I'm going to pulse the wave one more time. I'm going to trigger another wave, and what I want to see is I want to see the interaction between this wave and the wave afterwards. So I just press another pulse here. Sorry, it's a little bit too fast. Let me see. Okay, we need to restart here. Let's try again. Okay, so pulse, no damping. I'm going to pulse it. Let's do slow motion, loose end. Okay, so let's pulse it there. So what I'm going to do, that one there is going through a loose end. It's going to stay on the top, and I'm going to pulse it here. This time what I have is I've now created two different waves. I've just generated my second wave here. This triangular wave here is on top. It's now traveling to the right. This wave here was my first wave. It had hit a loose end here, and it's now reflecting back the way it came. What waves will do is they will actually interfere with each other. Sometimes when they interfere, they help each other. Sometimes when they interfere, they actually harm each other as well. Later on, I'm going to show you exactly what happens here, but we're just going to watch on the simulation here. As these two waves here steadily get closer and closer, what's going to happen here, we're going to see this is the first interaction point. Take note of the amplitude at this point here. It's about yay high. As we step it closer and it gets higher and higher and higher like this, you'll notice we actually get higher than the amplitude of each individual wave here. When those two peaks are actually right above each other, it's like one wave is here and the other wave is here. You notice they're going to do what's called constructive interference. They're going to actually add to each other and they're going to actually go higher than they were before. As they pass, however, they're still transmitting energy. There's no permanent displacement. We're going to eventually have our two waves go out from there. So let's just step across here. Let's watch one more interference reaction here. So here's our setup. We have our wave on the bottom. We have our wave on top. This wave here is going to the right. This wave here is going to the left. We're going to watch interference again. This time, they're actually perfectly going to destructively interfere. This guy is trying to take the amplitude positive. This guy is trying to take it to the bottom here. As I slowly step close to the window, as these two waves here interact with each other, they cancel each other out, and you'll notice that the net wave that we see, eventually the wave here would have been here and the wave would have been here. When those two amplitudes, positive and negatives, add up, we end up actually getting a zero wave. So that would be a perfect case of destructive interference. There's no permanent displacement, so the waves would just transmit past it. If there was no dampening, okay, that was a perfect world here, we'll still see that the waves continue onwards. So that's something cool that we can see for waves. We see what happens at a fixed end and a loose end. Fixed end, there is some reflection. Top goes to the bottom. At a loose end, there is no reflection. What we're going to switch over here is to yet another simulation here. This is on wave interference. This one here starts off with water waves. We're viewing this one here from top view. For this simulation here, you can press this on button. Just like the oscillate button here, I'm going to get droplets of water that actually go up and down like this. For water, we can actually switch over to the side view here. As this wave here is happening, I want you to note the bright blue bands and the darker black bands here. One thing I'm going to watch for here is when I switch over to the side view case. Let's see if I can do side view, or maybe that's just pulse. Well, I was supposed to be able to switch over to the side view case. Another way I can see the side view is I can actually track. I pull out a meter. This can actually sample. Imagine this is a side view look at the water. I'm just going to put one of these detectors inside here. Let's let it pulse here. All right. So far the water wave hasn't reached this part here. I want you to just track what happens to this. The darker black band is what happened first. My meter is going to sense how tall that dark band is. The dark band is actually going to represent the bottom portion of that sinusoidal wave. That's going to be the lowest point. We're going to hit the trough. As we keep stepping across, the wave pushes past me. We're going to go into the bright band, and we're going to end up having the higher. This is now going up to the crest, and because this is pulsing here, it's just going to continue to create a sinusoidal wave for us here. What I want to show you here is we're going to represent this on the next lesson. These brighter bands are places of constructive interference. It's when the waves there help each other. And when they help each other, we have what's called a wave front. So even though I am looking on this from the top, I'm marking off this is a circular wave here because the droplet hits the water. It spreads out in equal directions on every direction there. And basically what happens here is I'm tracking the tops of the waves as it goes through. Everywhere where I look, whether it's over there or whether it's over here, sure, it may be slightly out of phase because of where I actually am away from the source. Both parts of it will actually get the sort of top of the wave, bottom of the wave. In a similar fashion as before, I can increase the frequency. I can increase the dripping speed. We should see eventually these ones here get closer and closer, right? They bob up and down quite a lot more. The amplitude here, I'm going to cause the droplets to push down a little bit harder. You notice a little bit difference in intensity here. The amplitude is now larger. I can decrease that amplitude as well. As those the pulsing of the water here gets a little bit not as intense, the water level doesn't oscillate back and forth as much. So that there's sort of the wave analogy. What we're going to do here is we're going to switch over to another example. So this is with the water wave. We'll switch over to the sound wave example. So this is a sound wave. I have a speaker. Same thing that's going to happen here. I'm going to cause it to oscillate. This is going to cause me those wave fronts here. We have sort of dark band, bright band, just like before. The frequency is actually always delivered by my source. I turn my volume up. Let's see if you can actually hear the tone of this one here. Right. Sorry, that's a little loud here. Let me see if I can decrease that. So I'm going to decrease that one there. Let's play the tone. Hopefully, I don't know if you can hear that through my mic here, but that one there is the sound that this speaker is actually going outwards at it. Remember, there's two ways this wave here can actually change the amount of energy it's carried. So I can play around with the amplitude. This plays around with my volume. So I'm going to play the tone again, bar your ears for a little bit here. So plays the tone. I can increase the amplitude, so increase the volume. I can decrease the amplitude, so make the sort of metaphorical water waves here not be as intense. You'll notice in the sound analogy here, we're actually getting a more lower volume sound. The other way I can do it here is I can change the frequency of the wave. In changing the frequency, like we saw before, right now the wavelengths here are fairly wide. The crest-to-crest distance is fairly long. As I increase the frequency, we're going to hear what happens to the sound itself. So higher frequency. As I go to lower frequency as well, we get a lower tone. Okay, so in waves, right, you see that the frequency for sound actually gives us the tonality, the different note that I get. Amplitude gives me the volume. Right, so that's there for the sound analogy. For the light analogy here, in a similar fashion, I can play around with frequency and amplitude. Thanks for barring with that sound there. So I'm going to turn on this laser here. This laser here, again, all the bright regions are demonstrating places of constructive interference. I have my meter here, which could demonstrate the sort of metaphorical. They're actually measuring the size of the electric field here. This is also going to be a sinusoidal wave. Again, I don't know if this mentions any dampening, but that's sort of the sinusoidal wave here. I can play around with the amplitude. Unlike the sound analogy where amplitude was volume, we're going to see if you can track what happens here. So there's the amplitude. If I decrease the amplitude, we're going to see on this part here, the size of the amplitude when it finally reaches my detector will actually be a little bit lower, and it's actually getting a little bit less and less bright. It's getting a little more dull. As I increase the amplitude, I wait for those waves here to make it to my detector. The wave itself, the electric field here, oscillates up and down a lot more, and you'll notice that the brightness actually has changed quite a lot. So amplitude in the sound analogy has to do with the color intensity, the brightness of it. Frequency here, instead of changing the tonality like the sound did, I can change the frequency here. I can change it from like higher frequency here would be a higher energy light. Let's move this detector here closer. We're going to actually have like a blue wavelength like that frequency. Let's send in some red wavelength here. Red is a longer wavelength. I don't know if you can track it there, but the crest to crest is a little bit longer. So in changing the frequency on it, we're actually changing the color of light that we're actually seeing. This is still just the visible portion of it, and the visible portion is between 700 nanometers to 400 nanometers. Just to end off with these simulations, you can definitely play around with this a lot more by yourself as well. We can look at interference. Interference here, they're doing the water analogy, but this time I have two taps. Interference is sort of like that slinky analogy we did before. It's like we're sending one wave in, another wave in. Sure, it's a little bit different because we're now circular waves, but let me just run the clock here so you can just sort of appreciate what's happening here. So I'm going to run both of these here, making sure both of them are on. I'm going to pull out my graph detector here. So what's happening is each of these water waves here is generating an amplitude, is generating a sort of the water level is going up and down. But as these waves here interact, this time here in 2D, there are places that both of them destructively interfere. This is now actually a darker band than before, and there's brighter bands as well. That's a constructive interference case. Same thing happens to sound and light. The other cool thing that happens here for these experiments here is going through a slit. So what's going to happen here, I don't know if you've ever seen a water tank. Basically, it's a motor, it's a generator. One key thing I want you to see from these phenomena is the motor itself sets the beat. It sets the frequency. What's going to happen here is we're going to start off actually having no barrier. So this water generator here, I'm going to increase the frequency, so it actually bobs up and down quite a lot more. So I'm going to pull up my meter so you can see that. Again, my meter here is showing the side view picture of it. So this is the frequency. I'm at a slightly higher frequency. This generator here is making waves here at quite a quick speed. What's going to happen is there's no barrier. Now what I'm going to do is I'm going to introduce a barrier of having one slit. At first, you would imagine here water particles here, well, they have they're physical, they have mass. They shouldn't be able to go through a physical barrier like this. Because water here is actually carrying the energy in terms of waves, you would imagine that this band here that's not aligned with the slit, that part there would be able to get through, but none of this extra water actually gets through. We're going to run the clock and we're going to see what happens here. you'll notice, sure, there's a lot of the particles that were not on a collision course with a slit. Those ones are able to get through, but it's almost like there are other slight water particles here that are actually managing to twist around the corners, giving you a nice circular wave afterwards. That's a little bit more dramatic if you can play around with the slit width, so I can make it a little bit more narrow on it. You can hopefully see that circular band a little bit better. I can even do a double slit experiment. So again, water is somehow having some wave nature to it. It's able to sort of wrap its way around these walls here, and then again we get that constructive destructive indifference from before as well. Just to finish off the simulation, you can play around with the diffraction of light as well. In the case of light here, I can turn on my laser pointer. There's a tiny slit here. I can play around with the shape of the hole, and just like with the water analogy, I would imagine light is supposed to go directly through a circular shaped hole. It should just be giving me the circle, but the light that's slightly around it ends up bending around the circular corners, and we end up seeing this nice circular pattern. If it's a square, it changes to that pattern. We can change the wavelength, change what happens to that there. Similarly, we can play around with the width. So this one here is the width of the square here. Let's go back to the circle. So that's the pattern. Let's go to a brighter color that you can see. So I can play around with the diameter of the circle. You can see the difference in, this is called the diffraction pattern. Diffraction means wrapping around. In that case there is just showing to you what happens afterwards. So that there is some phenomena. I'm going to just sketch out some of these phenomena for you in tomorrow's lesson, and then we're going to look mainly at two different phenomena for the next couple lessons here, mainly looking at reflection and refraction. Thanks guys, take care.